Here's a data sheet for laser module I'm working with, and I want to start working with it, but there's a little bit of a caution before we start doing that. We need to be careful with how this thing is installed. So for operating the TEC, the housing must be connected to a suitable heatsink. The cap is no heatsink and not suited to be used as a contact. Only use the bottom of the base plate for this purpose. And if we look at, here's the drawing, just to sort of illustrate, I think it's kind of neat on this section here, what it looks like on the inside. So there's a base plate, the TEC is attached here, and we have the laser diode right there. So how do we attach this to a heatsink or design a heatsink so that we extract enough heat from this appropriately? I started with an initial pretty simple design. Mostly I designed this around, okay, we've got 440 screws. The laser diode is going to be inserted here, the module, and I want to have some contact with the base of the TO5 can and, the fixture. And so this will see right here, laser will go in, laser will go in, this piece on top, screw in with 440 screws. And so that's the thermal contact that it'll be making. Then later this PCB will go on top of these 3 dowels here to create a flat surface. That's for the PCB, but just kind of showing what the assembly looks like. And so I started with this very simple piece here. So then the question was, okay, well, I've worked with these kinds of laser modules in the past, but not this one specifically. I've never had to design my own heatsink, but I thought, okay, well, do I actually have to design a full-on heatsink, or is this small plate sufficient to extract the heat that we need? Is that the laser module itself? I mean, I think it outputs max, I think like 10, on the order of 10 milliwatts. So it's not a super powerful laser, but want to make sure that it stays healthy and thermally healthy. And so the question is this simple plate enough to dissipate the heat that's produced by the laser module? Here's a simple model, heat transfer model. It's essentially a thermal resistance stack to at least get a understanding of what the thermal heat transfer processes that are happening. And so we've got the TO5 can, laser diode inside in this base. And so that base is what interfaces with our fixture. Now, the thermal resistance associated with that is going to depend on a few things, primarily the contact between the fixture and the base. So the flatness of the fixture is going to matter. Thinking about likely we'll use a thermal paste to help with the heat transfer. And so that's going to vary considerably depending on how I calculate that conductance. And so that's why there's such a large range with 2 to 40 Kelvin per watt. And the through hole on this fixture is only about 7 millimeters because the base of the TO5 can is about 9.5 millimeters. And so it just gives a very small ring of thermal contact that will allow the heat transfer to happen. And so on that surface or that fixture, that plate, there's going to be essentially more aluminum surrounding it. So it allows for clamping force using the two 440 screws, and that's where that thermal resistance comes from. Now, we want to evaluate this based on, the sensor's going to essentially operate in outdoor conditions. Won't expose it to rain or anything like that, but we want to make sure that it can go up pretty high in temperature and still be okay. So want to evaluate this at 50 degrees C. And so the question is, okay, based on, let's say it gets really hot, we need to run this sensor. What is going to be, so the question is, what is the temperature at the base here, given an environmental temperature of 50 degrees C? So that's essentially what we're looking for. And it really comes down to, there's the interface resistance and then resistance to the environment. And so that comes in different forms. There's convection from the surrounding air, radiation into the environment, and then really, there's cage rods attached to this fixture. There's other dowel pins, for example. There's other parts that can help with the heat being generated from the TO5 can. So let's look at what these equations look like. Okay, so the model essentially is broken down into what's the cooling effect and heating effect. Cooling effect from the Peltier, the TEC, and the heating effect from the environment. And so we try and balance those two. And essentially, it's there's this S coefficient that we have to solve for, which is a Peltier coefficient. This is just joule heating, and then your standard Fourier type heating factor associated with conduction times delta T. So this is the QC, Q high, and so if we make a power relation here, we can solve for voltage. Let's see here. Okay, so then we start looking at certain conditions that allow us to make some assumptions and start. Really, what we're trying to do is solve for S, that coefficient there. So when the cooling effect is zero heat transfer, steady state, and if we take the derivative of this relation delta T with respect to the current, we can solve for what the relationship is in the condition where the current is its maximum, Imax. If we plug that back into the delta T max relationship, then we can we essentially arrive at this expression, and then allows us to solve for V max. And so V max, then we can start, once we know what V max is, we can start to look at data from the data sheet and start plugging that in. And so that it finally allows us to solve for that S value. That then allows us to go back to the Imax relation and solve for R, and equally for the K value. And so why are we doing all this? Essentially, it's we're trying to arrive at what a Qmax value is. What is the maximum heat being dissipated here, heat transfer occurring. And so the model tells us that we're looking at something like 0.686 watts. And from the data sheet, the Qmax at delta T equals 0 is 0.68 watts. So that's kind of how we essentially convince ourselves that the model that we have is consistent. And so then what we're trying to figure out is, okay, given an ambient condition, so temperature of 50 C outside, let's say it gets really hot, we want to operate this sensor continuously without having to worry so much about the temperature. Does that 50 C ambient condition fall within that 67 Kelvin Tmax from the datasheet, delta Tmax? And datasheet essentially tells us what is the maximum temperature difference at Q equals 0, and it's 67 Kelvin. So given this 50 C, are we falling within the 67 Kelvin? Okay, so does this 67 Kelvin budget allow us what we need to be able to operate the laser with this heatsink is essentially the question. So one simple way of looking at this is, okay, we've got T high minus T ambient, T naught is equal to the heat transfer from that T high times the thermal resistivity of the sink overall, the heat sink overall. And here the Q high is the cooling effect plus the power from the TEC. So if we work that out based on the data sheet for this system, we can arrive at essentially there is some heating due to this TEC. So if T naught is equal to 50 degrees C, T high turns out to be 55 degrees C. So the delta T that's required by the TC is this is the set point of the laser. So, or 30 Kelvin, which fits within this Tmax, delta Tmax budget from the datasheet. So, in an effort to keep this video from going any longer than it already is, there's a lot of assumptions that were made here. Kind of rushed through some of the calculations just because this video is already getting pretty long. But if you need any help with figuring this out for your own system, more than happy to help. Please reach out at redwoodlabs.tech. Schedule a free call, and we'd love to help. So what does this mean for the design of this heatsink / fixture? Effectively, it means we don't have to add any fins, and the very simple plate design on this is sufficient to keep the thermal budget that the datasheet calls for on the laser module, which is great news. So we can keep it simple. Fortunately, it's not producing a lot of heat, and so we don't have to get too complicated with this. So, long way of saying this this plate is good enough to use as a heatsink. Thanks for watching.